Okay, how are you today, guys? I hope you are doing well. So please stay safe. And for your informations, in the next 2 weeks, we're going to have assignment one. So I hope that everyone is ready to take the assignment one. Assignment one is one of form final exam assessment replacement. So I hope that this will be covered for the covered marks for course. I mean for the test that you had taken in previous week. So without due further, let me share our subtopic contents this morning. We be on subtopic 2 in the topic 3, slope stability. So for those who has familiar with my style, I will not wait until the class full for numbers of 50 such as, because my clock is starting clicking at 10 a.m. So I have to start now. So those who's coming late or who suddenly appear, so just be prepared or be ready to have additional notes by your own initiative. And other than that, before I forget, I would like to attach these two hands out that I'm going to this morning class. So while we had these online sessions, so I hope that you can have through these hands up also. Okay. Okay, now there are two additional notes in the meeting chat room, so you can download it and take a look from this content. So as you know, this will be still in the slope stability for subtopic 2 in the week 9, which on slope stability analysis. We're going to analyze the stable of the slope by different methods of analysis and some theory or formula involved. And to the outcome of this sub topic learnings, what me expect from you is that you are able to analyze the slope stability. And these are the contents of the subtopics for this week is definitions on factor of safety, the stability analysis using total stress analysis, and the stability analysis using effective stress analysis. So in the previous class, I have mentioned to you the situations and also the appropriate strength parameters to be taken in considerations while you are doing the design and analysis of the slope. So using the appropriate strength parameters with appropriate conditions of the slope, we expect to have the value of factor of safety, it's around 1. If you have the FOS less than 1, so we may consider the slope in a stable, the slope in a critical condition that may prone to fail. And what's exactly factor of safety? So by definitions, it is a ratio. It's a ratio between the available shear strength and the acting shear stress of possible sliding surface in the slope. So the definition itself, as you can see here, it is rely on the strength of the soil. So the strength of the soil is very important when you analyzing it uh, in additions to the soil properties and the slope angles. So in this case, by having the shear stress that can be calculated from the Moore column formula, you can check the value and in comparison between the shear strength and the shear stress that will tells you the factor of safety. Lower part of these slides shows to you the formula how to calculate the FOS. So the FOS is maximum shear strength over to the shear stress. So as I explained in the previous class, we have many types of slope failure, such as we got some kinds of slides failure. We also have planar failures. We have also flows failure, and we have also the wedge failures. So all those failures shows to you different slip circle, such as if you have slide failures, that will going to give you some sort. I mean that if you have a planar failures, that the slip failure will be in parallel to the surface. And if you have some kinds of rotational failure, that will be giving to you some sort of the circular slip surface. So the recommendation value FOS to be taken as your reference when you analyze FOS, such as for end of construction slope. This is recommended value FOS is 1.30. Meanwhile, if you are dealing with the steady seepage conditions, the FOS is 1.25. So these are the ideas to ensure that to check whether the analysis you have done is correctly or incorrectly. If you are dealing in problem involving with the support to buildings, the recommendation FOS is a 2 to 2.5. As I said again, the failure of the slope can be considered due to some cases or some factors such as additional loading, and then we have the water table effect, we have the erosion, we have the some sort of earthquake. So these are the factors trigger to the slope failure. Again, some now when you have some kinds of recent development, the housing trend located on the hilly sides. So this is the best value or the best FOS as reference to be taken in the design analysis when dealing with the building on the hilly slope or hilly sides. So you can see that the value recommended FOS for these kinds of application is higher compared to the FOS in end of construction, the steady seepage conditions, and also the natural slope after long standing. Again, I think that this question is quite similar. I mean that this last statement is quite similar to the previous question in your comment test. Why was the FOS in the foundations is higher for building compared to other than that? Because of this is where you can have that the additional loads that you apply on the foundation itself, and then if the foundation lay on the hilly sides, so the value of FOS must be taken larger compared to the other applications. And then when we go to the next one, it also explains to you the mechanism how the slope is failed. So look at to this one on the movement of soil weight W. So the rotations of the slip circle due to this weight of the soil mass is calling as is a disturbing moment due to disturbance force that that coming from the weight of the soil multiplied with the level arm or perpendicular distance where the W is at. And at this time also, we also have the resistance force that is due to the shear strength of the soil CU, similarly to the length of the arc. So the length of the arc along the slip circle, the slip surface, together with the undrained cohesion that try to resist any slope mass movement. So that's come to the formula FOS is equal to the maximum shear strength over to the shear stress, or by other definition the FOS is considered as a restoring moment over to disturbing moment. Later on I will show to you what are differences between the restoring moment and the disturbing moment. Again, on this part of informations tell you when you are dealing with the short-term stability, you have to choose the right strength parameters in your analysis. For example, when we analyze for shear strength, for undrained shear strength, this can be considered as a short-term stability. And the parameters of the soil at this stage, we are going to use the undrained C. What does it mean by this time? And during this time, we assuming that the little drainage take place to occur by the U pore water pressure is taken as a 0. Meanwhile, if you are having a long-term stability of existing slopes, so during this time, we allow for drainage to occur and take place, and we can measure the U, the pore water pressure effect. And at this moment, the recommendation, the strength parameters need to be taken as a drain strength parameters, effective C and also effective V. And also for the last statement here is similar to the previous class explained. If you have a slice along pre-existing slip surface where large displacement have occurred, the residual shear strength parameters should be used. And for stability of the slope, to check whether the slope is stable or not, so we're going to calculate FOS. The simple thing is that the indicator to ensure the slope is stable by look at to the value FOS. If you have FOS more than 1, so we can consider the slope is stable. Meanwhile, if you have the FOS less than 1, so that the slope is in stable conditions. And again, the shape and location of failure is not known prior by by using the try and error method to find the minimum F. Or it means that we have to design the critical slopes, the critical slip surface of the slope. The critical of the slope, it means that the FOS is equal to 1 or less than 1. So this going to consider under static equilibrium conditions by having two-dimensional analysis. For the complex problems, the slope stability can be analyzed in the 3 dimensions by different methods. We call it as a finite element method in the finite element program. As I said, the complex problem involving with the different soil parameters and involving with the pore water pressure effect, the water table, in also additional loading that apply to the slope. So at this moment, at that time, we couldn't analyze as a limit equilibrium method. Somehow it can, but need to use the advanced computer technology to analyze the problem. So these are the examples of the failure for slope. We have the planar failures, we have the circular failures, we have wedge failures, and the last one is the complex failures. For planar failures, it can be categorized into 2 infinite slopes and also the finite slopes. So for infinite slopes, we have small depth, long failure surface. Meanwhile, for finite slope, we have a simple wedge. This one just refresh what we have learned in the previous class. Same goes to the circular failures. We have 3 types of circular failures. We have base failure, we have tool failure, we have also face failures. And the next one is the wedge failures. This is involved with a multiple planar failure surface. And the next one is the complex failures, combination of planar and circular. And we go next to the type of stability analysis. For this time, we can see that the slope stability analysis can be done using the 2 different procedures or 2 different methods. First, we can adopt by using the mesh procedure method, and then the second one we can adopt using the method of slices. What are differences between these 2 methods or the procedures? The mesh procedures is when you have the mass of the soil above the surface of sliding is taken as a unit. And then this procedure is useful when the soil that forms the slope is assumed to be homogeneous, although this is not the case in most natural slopes. And in comparison to the method of slices, the soil above the surface of sliding is divided into a number of vertical parallel slices. So the stability of each slice is calculated separately. This is the versatile technique in which homogeneity of the soil and pore water pressure can be taken into considerations. And then it is also account for the variations of the normal stress along the potential failure surface. So for your level or in this class, we only concentrate to this type of the method by using the method of slices. Actually, you can analyze slope using the mesh of procedure, but it's depending on the situations lah. I mean, if you have simple homogeneous soil profile, so the best one using the mesh procedure because we don't need to divide few vertical slices. Meanwhile, if you have a heterogeneous soil profile, and then there's involved a lot of soil parameters, so the method of slices is the best option to be taken in your analysis. Okay, next we move to the stability analysis using total stress analysis by method of slices. So these are the features categorized under total stress analysis. It is also known as a short-term stability, and this is end of constructions during and immediately or newly cut constructed slope in a fully saturated clay, and the little drainage to occur. Undrained shear strength parameters need to be used, where the Phi-U is 0 for fully saturated clay, and if you have the undrained C and also the undrained Phi. So how do we know that? We need to use whether it is GSA or ESA, look at to the problem statements. If the problem statement says that you have to find FOS immediately after embankment is constructed, that means you need to using the undrained strength parameters. If you have a problem statement says that calculate or check the stability of the embankment slope after 10 years is 10 years constructed or 10 years construction has been done. So it means that is a long-term stability analysis problem. So the next thing is the conditions where we can adopt all those analyses, such as homogeneous slope, and then we have heterogeneous slope, and then we have the tension crack, and the next one is the submerged slope. So what is a homogeneous slope? Homogeneous slope, by simple thing to understand, is that when you have the physical properties, the properties of the soil is similar. Let's say we have single layer of soil, so we can consider it as a homogeneous slope. If you have multiple layers of soil on the slope, so we have a soil type A, we have soil type B, so that the slope is categorized under heterogeneous. Somehow, when you have slope which made material from fully saturated clay, the slope prone to have tension crack, and also it also has to be considered when you get the submerged slope problem. So the analysis will be differently according to these four conditions. Okay, look at to this total stress analysis. The total stress analysis is actually be applied to the case of newly cut or newly constructed slope in a fully saturated clay, and the undrained shear strength being shear stress is equal to undrained C. It is assumed that the failure surface will take the cross-sectional form of circular arc, usually referred to as the slip circle. The center of the critical slip circle will be somewhere above the top of the slope. So the critical failure slip circle is one of an infinite number of potential circles. That means you have to do few trial and errors to find the most critical one. If you look at on the left figure here, you can see there are many potential slip circles created at this slope, because we are searching the most critical or the most minimum number of FOS. So in the slope stability, what we actually doing is that we need to design the most critical one. If the most critical one is safe, then whatever slope geometry comes to you, that will be also considered safer, stable. So in this part, at this moment, you have to find where is the center of the slip circle that produce to you the minimum number of FOS. And the critical circle is the one along which failure is most likely to occur and for which the factor of safety is the lowest. A number of trial circles are chosen and the analysis repeated for each until the lowest factor of safety is obtained. So a lot of processes involved just to ensure which point of the locations tells you the critical one. And then in total stress analysis, this figure on the right side indicate to you the cross-sectional of slope together with a trial slip circle of radius r and the center O. Instability tends to be caused due to the moment of the body weight W of the portion above the slip circle. As previous slide, this is the body weight of the slope W. Along the slip circle from OAB, this along the slip circle arc, here is a restoring forces coming from the strength of the soil Cu, and also the length of the arc, which is r theta. So when you are taking moment at O, the W and D is forming a moment, which is a destabilizing moment, or we call it as the disturbing moment. At this time also, when the soil mass prone to move or prone to rotate in these directions, there's another resistant force resist from the movement to occur, which coming from the Cu and R theta. So the deriving from this formula is showing to you that the disturbing moment as a WD, so the tendency to move is resisted by the moment of the mobilized shear strength acting along the circular arc AB. So the length of R from A to B is equal to R theta. So the shear resistance force along AB is a Cu R theta. Therefore, the shear resistance moment is equal to Cu R square theta. So the shear resistance moment is a Cu_r square theta, and we have the disturbing moment is a Wd. Therefore, the FOS calculator is as you see here, Cu_r square theta over Wd. So the Wd is the disturbing moment. Meanwhile, on the part of it here is a shear resistance moment. So what is a W? W is the volume of the unit weight above the slip circle. So it is the area times with the unit weight of the soil. So by explanation, I hope that you can imagine how it means that one slope or one weight of soil tend to move in this direction. At the same time, the other forces, what we call it as a restoring force from Cu and R theta, try to resist a moment coming from the weight of soil. And the next one shows to you is the conditions where we try to analyze total stress analysis for different conditions, such as we have the embankment or tip, figure A, and then we have the cutting in stratified deposit B, and the next one is the effect of underlying hard layer. What it shows to you is that the extending formula when we consider all the cases here, and also the situations when we have these kinds of A, B, C, and D, the created slip circle will be different accordingly to the conditions A, B, C, and D. For example, for the A, effect of underlying hard layer. What happened to the shape of slip circle when we have underlying hard layer? So for figure A, when we have the hard layer at the bottom and then upper layer is a soft, so it is given to us that the kind of two failure. And you see that the slip circle is end at the two failure. Meanwhile, if you have a stratified soil, heterogeneous slope, which consists of soil A is a soft, and then our bottom layer is a firm soil, and you can see that the slip circle is extended beyond the few meter ahead in front of the two slope due to the existence of the hard layer here. And in the calculations, the factor of safety S is equal to R square times Cu theta A plus Cu theta B plus etc. If you have many soil types, so this formula is extended. Same goes to the disturbing moment Wd. And the next one, if we have a tension crack effect. So what's about the calculation FOS, the calculator FOS? Of course, when we have the tension crack effect, the circular length R above here will be taken as a 0 because there is no shear strength at these portions. So the strength or the resistant shear force coming from the mobilized shear strength is reduced due to also the theta, the slip circle angle reduced. And it is stated that in cohesive soil, the tension crack tends to form near the top of the slope as the conditions of limiting equilibrium. So there is no shear strength can be developed in the tension crack, but it can be filled with water. Allowance must be made for hydrostatic force Pw, which acts horizontally, adding to the disturbing moment. So this time you can see that the PWYC is another component in this formula at the disturbing moment. So the FOS is equal to CUR square theta over WD plus hydrostatic force times with the perpendicular distance YC. So the YC is considered from the 2/3 of the Z naught plus with the height from top of the slope to the O. That's we calculate the YC. And you can see that here the effect of the tension crack is reduced, the theta becoming to the theta C, and then the length of the arc above here at the tension depth is taken as a 0. That's why you can expect that the value of FOS is getting lower supposedly. If you have this one bigger, so the FOS supposedly lower. And then the next case, when we have a submerged slope. So the submerged slope, if you look at to this figure, the equilibrium of the moment of the force is taken same or is considered as a 0. Equilibrium at this point, at this form side is equal to at this right side. The left and the right sides equilibrium conditions of the moment taken by this case for submerged slope. So you can see from here that the moment about O of the mass of water in the half segment EFH at the left side is equal to the moment at the right side FGH. Thus the net pressure moment is considered as a 0. So the weight of the soil mass, if you have above the water level, so the unit weight of the soil will be taken as the bulk unit weight. Meanwhile, if you have the soil below the water level, so we have to consider the submerged unit weight as a gamma soil minus with the gamma water. This is one example for case when you have a homogeneous slope and then also have the effect of tension crack. We need to calculate the FOS for the first case without the effect of tension crack, and then calculate the FOS with the effect of tension crack empty of water, and the next one calculate the FOS with the effect of tension crack full of water. So as you see from this example, the W is taken as one single unit. By looking at these solutions, we know that the procedure of the mass is taken in the consideration to have the FOS value. Because of what? You can see that the W here above the slip circle is not taken or is not divided into equal or into parallel vertical slices. So thus the W is considered as a one single unit mass. So this moment at this example, it took the mass of procedure to analyze the FOS. Okay, first of all, when you have these kinds of problem, we need to find the radius. Why the radius is important? Because you see just now in the formula we have CUR square theta over WD. So the R, the radius of the slip circle, can be considered from the theorem Pythagoras formula, and then the sector angle, where it is measured the sector angle. So you can see from here there are two sectors angle. The first sector angles without having the tension crack, which OA and B. Later, the sector angle after having the tension crack is reduced from OAB become OAC. So you have to be careful when you have these kinds of problems, whether you have FOS without tension crack effect, and the next one you have FOF, you need to calculate FOS with having the tension crack effect without water, and then allowing for tension crack with a full of water. It's very important to check closely the parameters involved, the right value to be considered in the calculations. And when you have all those parameters, you substitute into this formula. So first of all, we can have the FOS is 1.44. Automatically, we can say that the slope is stable by checking the FOS is having 1.44. The FOS is a unitless. Please make sure when you write down the answer, there's no unit next to it, next to the figure number. And the next one, you need to calculate the effect of tension crack empty of water. So as I explained just now, so the sector angle reduced to the 67.44, and same goes to the area of the soil mass is reduced, and the centroid of distance from the O is also reduced. Thus, the calculated FOS, as you see here, is around 1.84. And the next case where we have a tension crack full of water. At this time, you need to calculate the hydrostatic force PW. So the PW is taken from the formula is a half times gamma water times Z naught power of 2. So the calculated hydrostatic thrust is equal to 91.54. So you need to find out what is the YC, so that we get the YC is a 9.58. Substitute into this formula, you can see that the FOS is a 1.65. So the FOS from the second case and to the third case is showing to you the lesser number of the value. From just now 1.8 something, and then it reduced to 1.65. Because right now we're having the hydrostatic force adding to become as a disturbing moment. How about you need to analyze the problem using the method of slices? Same goes to the process. As you can see here, the single unit weight W of mass is now divided into equal vertical slices. Just now we only have single W1. But then when we divide all the soil mass above the slip circle into few vertical slices, so the single W become into the W1, W2, W3, W4, W5 and W6. It is recommended to you to divide the W into equal width. For example, from here to here is a 2 meter, and then the width for the next slice, vertical slice is same as the 2 meter. Same goes to the final one here. The formula is still same. The only difference is that you need to tabulate the table to find what's the final answer for shear resistance moment and also to the disturbing moment. Right now for D is not considered as a single D. D need to be taken differently to each of the vertical slice. For example, if you have W for this slice number 1, the centroid for W1 is acting is 1/3 from the base. So you have to measure the W of slice 1 to O. So what is the vertical distance? And then same goes to the W2. Let's say you have decided that the width of the slice number 2 is a 2 meter. So the image of this slide W2 is such as a square. So the centroid of the W2 is a half of the 2. So 1 meter from left, 1 meter from right is the locations where the W2 is acting. So that you have to measure the horizontal distance for W2 act from O to here. So what is the D? And then you tabulate the table, you calculate W times D, so you can have the disturbing moment. So actually this is supposed to be as a D, it's not as the okay, that is correct lah, D. So I substitute into this table, you can get the final one. For your information also, the B, H and A, since we want to calculate the A is the area of the interslice, vertical interslice. So such as if if you have the right formula, you can get the accurate factor of safety. For example, look at to the slice number 1 here. We can say that the slice of the W1 is such as triangle. So we can use the formula triangle to get the area. If you set all those slices as one single formula, so we can say that slice number 2 some sort of trapezoidal, this one also trapezoidal. So let's say we assume all those slices as a trapezoidal formula. So the slice number 1 here, for example, just now I said triangle, it can be turned into trapezoidal formula by evaluate or by measuring the height of the left and right side of the slice. I mean that for H1, slice number 1 is a 0 because it is started at this point kosong. And then for H number 2, slice number 1, supposedly let's say 1 meter. So to calculate the area for slice number 1 is a half times with 0 plus 2 times with the width of the slice. So you can have the area for slice number 1. And then for slice number 2, if you just now considered here as a H2 for slice number 1, right now it is H1 for slice number 2 as a 2 meter. So measure the height of the slice number 2 at right side, let's say 3 meter. So in order to calculate the area for slice number 2 is a half times 2 plus 3 times with a 2. So we can have the area of the trapezoidal for slice number 2. The same process repeating for next slice 3, 4 until the end. So this is the case where you can see that there is no effect of the tension crack because the theta, the sector angle, is covering from OA to the N1 here to the uphill slope. Okay, we go to next to the slide. If you having these kinds of problem and you want to analyze it by method of slices, so for this case, we have dealing with the complex one, which is under formula or under theory of the Swedish formula. So in this kind, you need to find what is the alpha interslice angle as an alpha here, and then you have to resolve the W, the weight of each slice, into two components N and also to the components T. The N component, the component N, is called as the normal force at the slice, at the base slice. Meanwhile, the component T is the shear interslice force at the base slice. So the resultant from the T and N is the W. So when we resolve into T and N, this is what we have the formula. So the N is the W cos alpha, meanwhile T is the W sin alpha. So substitute this formula into these equations. Right now we have the shear resistant moment over to the disturbing moment as becoming to you CU r theta over W sin alpha. So this is when you adopt the method of Swedish. For example, cohesive soil. Okay, same goes here for cohesive frictional. So again, tabulate the table, get the summation T and summations N. Okay, now we extended the analysis to the short-term problem analysis using the method of slices. So these are the features tells you the situation when we can apply the effective stress analysis. So for the first of all, the effective stress analysis also considered as the long-term stability. So this is being used for existing slopes and embankment, spur and with steep, earth dam with a steady or intermittent seepage, where we allow for drainage to occur, and you can measure the effect of pore water pressure. At this time, we use the drain strength parameters, and you can see that the C effective and also the effective phi are taken in the calculations. So it's actually vice versa to the total stress analysis. So in effective stress analysis, there are two theories involved behind the calculations. The first of all is a Fellenius, and then the next one is a Bishop. So what are differences between these two theories? So for example, Fellenius, assuming that the interslide forces E1 and E2 are neglected, and then the resultant interslide forces are parallel with base direction to arc length, and there is no interslide normal force. For Bishop, the resultant interslide forces are horizontal, and then no interslide shear forces. Consider interslide normal force, the resultant of forces in the vertical directions. So the more complexity in the Bishop theory lah, if you look at after this. Okay, this is how the deriving of the Fellenius by using method of slices. When we taking the considerations for Fellenius, it is right now you can see the effect of the pore water pressure U. So at above here, you can see that for the pore water pressure is 0. For example, UL is equal to 0. So what is the L? L is a B second alpha, actually the missing point here. So the deriving of this formula is taken from here. You take one interslice, one intervertical slice from this soil weight W. So you can see that all those components interslide forces are deriving from here. So we have the internal vertical interslide force S1 and also S2. You can see that the S1 in equilibrium. However, the directions is opposite between S1 and S2. Same to the E1 and E2. But this case, for Fellenius, E1 and E2 is considered 0 because the method or the theory ignore the effect of the E1 and E2. But the deriving of the N and also T can be seen from here. The T components, which is the interslide shear force at the base of slice, as C as a T. Meanwhile, N, the effective normal component from this interslice vertical W, is taken as a N minus UL. The effective N is equal to N minus UL. At this time, so you can see that the effect of the pore water pressure, so UL, U is the pore water pressure, L is a B second alpha. So from this one, the base assumed to be straight of the line because as you can see here, actually we have this circular slip circle. But then when try to derive the formula by taking one small interslice W here, so we can assume that the base slice is a straight one. So all those component interslice forces are deriving to forming a FOS formula. So the complexity of the formula is deriving to you is that FOS is equal to C effective C LAB plus tangent effective Phi summation W cos alpha over W sin alpha. What is the alpha? Alpha is the interslice angle between W and N. So that's how you find the alpha. And then what is the L? LAB, capital L. Capital L is the length of the arc. So that is equal to the theta R. Again, forgot to mention to you, the theta is calculated in the radians unit. So then how to convert theta into radians unit? So for example, if you have the theta is 50 degree, so to change in the radians, 50 over 180 times with a pi, so that you get the theta in the radian. Okay, the next one, we couldn't see that we have some sort of there's no heavy tension crack effect. somehow we have to consider the analysis if we have a tension crack effect. So mostly it is occur in the cohesive material salt. So at this part, the considerations of the calculation Z node for effective stress analysis are totally different. So right now, you can see that the Z node formula is taken the active lateral earth pressure Ka in the equations. So the Ka is 1 minus sin phi over 1 plus sin phi. So you substitute in this formula Z node so you can have the tension crack. And the formulas are still same. We have the disturbing force. We also have the restoring force. So you convert all these things by taking the moment at O. So it is forming to you the shear resistance moment over to the disturbing moment with this kind of formula as a C effective L AB tangent effective summation C W cos alpha over summation W sin alpha. And for the next theory adopted in the ESA method is a Bishop. So check on this left side figure. This is how the formula is derived by taking few interslice forces components. The deriving on this part as shown here at the right side. So at this time, we can see that the E1 and E2 cannot be neglected anymore. So it is need to be taken in the formula how to get the FOS. Okay, the FOS for using the method of slices for Bishop theory. So it is assumed that the forces acting on the sides of any slice have zero resultant in the vertical directions. Dia terbaliklah pula. So now zero resistance in vertical directions. For equilibrium along the base of the slice, these are the components involved, such as assuming equal to 0. So we have W sin alpha minus shear stress at final over F times with L. So W sin alpha minus effective C L plus effective N tangent phi over F. So we are looking the F because we want to find the factor of safety. So rearranging the formula, this is the final FOS that we have. Let's say you are calculating the equilibrium in the vertical directions. So the formula is extended into the complex one, as you can see at the bottom part here. So I won't show you how to derive it. You can have your own time to check how to start off if you're taking equilibrium in vertical directions. So assuming total equal to 0, and then you derive from the W minus N effective cos alpha minus UL cos alpha minus tau F over FL sin alpha. Actually, in this, for example, if you have any textbook, you can see that for effective stress analysis, we might have the value for water pressure. Somehow we can have also the for water pressure is 0 if we assume as a 0. But then if you have the effect of pore water pressure, and then you have the groundwater level effect, so you have to take the considerations of U in the formula FOS. So cannot be neglected. But the deriving of the formula can be adapted directly from this formula. And look at to this example before we break 5 minutes. So this is one example of the effective stress analysis by method of slices. So you are given a slope with a appreciated slope height, and then the angles to find center of slit circles, and the informations such as unit weight is 18 kilonewton per cube meter, and then the string parameters are effective C 13 kPa and effective phi is a 30 degree. So you need to find and calculate the tension crack, and then calculate the FOS without the tension crack. Sorry, the FOS with tension crack effect without water, and then FOS with the tension crack with the water effect. One thing to remind every one of you is that for this time you have to get a graph paper, and then please have a set of geometry and some sort gentle leakage protector to assist you in analyzing slope stability manually, because for this assessment we evaluate you to find or to answer the question by your own calculations. So you have to draw slope geometry on graph paper and then find the R, get the sector angle, and finally calculate the FOS. So as you look at to these questions, is actually given the idea the method of slices need to be used for the FOS calculations. So as I said in the earlier lecture, we have mass procedure and we also have the method of slices. So example 1 just now showed to you the mass procedure method, and right now is a method of slices, and the next example shows to you the method of slices. But the next example I will let you to have your own, but I will explain on detail on the example 2, and my expectation is that you will have your own drawing, slope drawing, and recalculate the FOS so that you can have the understanding what I am talking today. Because remember in the assignment 1, we will cover topic 1 and the topic 3. Topic 1 is totally theoretical. Topic 3 we consist of theory and calculations. So don't take for granted. So when you go through the notes, please move your hand also to draw the slope problem and calculate the factor of safety. So first, how are we going to solve this problem? Okay, look at just a glance through, because later on I'll show you how to construct it. First of all, you have to understand what are informations involved and what kinds of the data input needed to tabulate the table. For example, here we have slice number, we have the width of each slice, and then we have the H1, we have H2, and we have the area of the slice, the unique weight, the volume of the W of slice, and then we have the alpha, we have the T component, normal force, and we have shear stress force as a T, shear stress as a T, normal as a N. And then because first question asks you to calculate the tension depth and locate the position of the tension crack, you have to calculate the Ka, and then you need to find the Z node. So Ka is straightforward. You just get the phi and calculate Ka. Same goes to the Z node. So we have the Z node, for example, 2.5. And the next one is you need to calculate the factor of safety without the effect of water. And the next is a full of water. Okay, how to analyze it? So these are the informations required, and some instructions, simple instructions for you to follow. You just go through lah. So this actually we begin with determine the angle of 26, and then from the horizontal uphill of the slope we open up the angle as 48. Once we have that intersections between 26 and 48 here, we can set the point of slip circle O. And then we need to measure what is the radius of the slip circle. For example, if you have the radius of the slip circle is a 10, so make sure the intersections of 10 at A same to the 10 from O to this point. So you can draw the slip circle at the intersections of point O. And the next one, you need to divide and the soil mass above the slip circle into equal vertical slices. On this part, we're going to assume that our scale drawing is taken as 1 centimeter equal to 1 meter. So at this part, when you draw the slope geometry, we will take that the height of slope is 8 meter is also equal as 8 centimeter on the graph paper. After dividing the vertical slice into equal width, and the next thing is that we have to determine the locations of the WX. Same goes to the interslice angle between W and the N. So the opening angle between W and N is the interslice angle. Since we have the tension crack effect, so the theta will be reduced to the theta C. Okay, next is how to calculate it. This is what I said. After we have divided into equal vertical slices, so we need to find the W for each slice, W1, W2 until the last W. And then the last slice here that affect with the tension crack, so the B of this slice will be reduced. So it's getting smaller. And then the theta C, the length of the arc at this position is considering as a zero strength. So that's why from the theta getting to the theta C due to having a tension crack. So formulate the FOS according to this formula. So you can have the answer FOS. So this is what seems to have calculated the tabulated table for each parameters to the N component and to the T component, the Z node and the Ka, tension depth. And the next one is the FOS. So the red circle here indicate to you the locations of the tension crack and depth. And the final one is the FOS with a full of water. So this is the positions where the hydrostatic force becoming as a additional component to the disturbing moment. Okay, the next one, if you have example 3 where we have a stratified layer of soil, so the problem shows to you different soil parameters for upper layer soil A and also for the soil B, and the sector angle of the layer 1 and layer B will be different accordingly to the slip circle. If the slip circle only covered for the upper layer, that is the theta for layer 1 for soil A. And then if the slip cover from here to here, that is the sector angle for slip circle for layer 2. So this is will be considered when you tabulate into the table. So you have to be careful when you analyze it. So the further solutions for this example 3 can be seen from hands up. Okay, let us break 5 minutes before I continue with the hands-on example. Meanwhile, you can have online game for a moment. Okay, I want you to join this. Okay, I want you to join this Kahoot game. So wait a second, we are looking the game pin here. Okay, log in this Kahoot game by game pin 1584607. Okay, I'm waiting for you to join this Kahoot game. Just around 5 or 10 minutes. Can you see the game pin?
Yes.
Okay, good. We may begin our game around 11, 5 minutes. Okay, total number our students this afternoon sessions is 36. 33. But our games player right now is 36. Okay, never mind lah. I think that you have too many devices. So this games is only for what we call it to refresh what you have learned in the previous course. So are you ready? Oh, the number keep increase. The number is increasing to 38. So I give you another few minutes before we start. Okay, I think that I'm going to start our game right now. Okay, this is on about retaining wall and slope stability. Are you ready? So, go. Okay. 10 answers, atoms from you all. So remaining seconds left for how many of you got right answer? It is Cabian walls. So 20. So you still not familiar with the retaining wall type. Okay, the winner is Aizat. Okay, good. Next. So we have 20 questions, eh? What is this? Okay, MSE wall. MSE wall will be covered in the last chapter 4. So our winner is, okay, he keep on the positions. The next question is, okay, same on the image. Quick wall. Okay, 27. Good. Okay, so far so good. Tasnim is the highest climber. Oh, before this, okay, true or false? Ranking KA is greater than column KA. Is it true? Yes, the answer is true. So KA is the active lateral earth pressure. Okay, we have new scorer, top scorer. Okay, ranking KP is greater than column. Is it true? Yeah, the answer is false. Okay, a bit balance between 22 and 19. So who is our top scorer? So Erin, good effort and good try. So the next questions on the earth pressure coefficients. So actually we only have Ka, K0 and Kp. Among these 3K, which one is the greatest value? Yeah, Kp. So, okay, she keeps on the positions. Okay, the answer is false. Next one. Okay, the other guys, please just participate to refresh your theoretical background. Okay, what is this? Yes, sheet pile wall. Sheet pile wall, the best thing is that it can be on the water to retain water. Okay, so good, Erin. So next question is distribution, the earth pressure distribution. Okay, quite difficult because only have 9 atoms answer. What's the answer? Okay, Steve Clay. So it will be seen in the next topic. Start here. Okay, next one. Okay, the earth pressure distribution will be used to calculate strut loads in for figure below, figure here. Okay, the answer is sand. Okay, 5 players just drop their answer. Next one. Okay, the earth pressure, still in the earth pressure. Okay, soft clay. Next is, okay, there's a changes in positions. So someone is climbing. Okay, for cantilever retaining wall design, moments are some about the Okay, the answer is the front two of the wall. Okay, our winner still Erin Yeager. So next questions on the slope stability. This is our topic this morning. Okay, the answer is what? Yes, slippage methods. Because if you notice, I keep on mentioning on the circular arc method, and then infinite slope method is also one of the slope failures, and stability number is another solutions how we can analyze the finite of infinite slope stability. However, this is not covered in our class. Okay, next questions. Yeah. Senang ya. Otak saya di kelas. Okay, the stability number method is only applicable for homogeneous soil. True or false? Yes, the answer is true. So as actually there are advantage and disadvantage certain methods. Okay, see that we have new scorer. Congrats. Which of the following represent the sliding force in the block failure analysis? This is also big tough one because it's part of complex slope problem. We only 8 answers until this moment. Okay, W sign alpha. Okay, good try. Which the following represent the stabilizing force from friction in block analysis? Okay, this is postgraduate level questions. However, you can try. Okay, the answer is W cos alpha tangent phi. Okay, the position has changed to Erin. So remaining 3 questions. What slope analysis method is illustrated here? Yes, infinite slope. Why infinite slope? Because you can see that the slope is long, limitless. So the next question is true or false type stability number NS is dimensionless. True or not? Yes, it is dimensionless. Dimensionless is a unitless. Okay, the next one is next question. Okay, still stability number method. How the FOS is calculated? How? You can guess and try because there's no cover in this morning class. Only can be found from book. Ratio between the given and required coefficient. Correct. Okay, the next last question. Is it true? Vertical exaggeration. Okay, the answer is false because as I said just now, it is you can use the appreciate scale to analyze it. Okay, we break a few minutes. Let's see podiums, our winner. Top 3 is a Zarif, congrats. And then second place is a Nazim Surabaya. And the last, the winner of this game is Erin Yeager. Congratulations to all the participants. Okay, ada lagi runner up, Aisyah. Okay, we're going to start next 2 minutes to see or to construct the slope by referring to example 2. Okay, you can have your own break while. Okay, shall we resume our solutions for example 2? Okay, this is where we have to start uh, our our step. Let's say we begin our step by drawing the slope geometry and the angle. First of all, if you look at closely to the hands-out example 2, you are given the 26 angle from 2 of the slope, and from the uphill slope, you have 48. And then this only the informations. Also, you are given the slope angle and the slope height 8. And first of all, what we need to do is that remember when we try to solve these kinds of problem, we have to draw on the graph paper, assuming that our scale is 1 centimeter is equal to 1 meter. So if you have a slope height is 8 meter, it means that on the graph paper we're going to have slope height as 8 centimeter. And also the information is given to you at the two of the slope, or the two of the slope. Let's say you start from here. The angle here is okay. This angle you need to find by determine between 1 to 2.15. 1 is a vertical and 1.5 is a horizontal. So the slope angle can be found using the tangents lah. But then actually the questions are given information the angle at this point as a 26. Okay, we have to measure 26. How do we get that 26? You have to use the jangka. You kena guna protector lah. You letak at this point, you buka sudut tu dengan 26 darjah. And the next one is that from the 8 meter of the slope height, uphill of the slope, you kena buka the protector angle with the 48 degree. Here is a 48 degree. So the intersections between 48 and 26 is the positions of the O, the center of the slip circle. Actually, they give the idea the center of the slip circle. From this here, let's say we mark as A to O, we can have the radius. How do we get the radius? You can measure using the ruler, such as, let's say our radius is 12 meter. So you letak ruler you dekat point A until O, you get the 12 meter. The next one is that you buka your jangka lukis. as a 12 meter. So you ukur lah on your jangka lukis from 12 cm. Jangka lukis you kat sini dengan sini as a 12 cm. So what's the important of that one? Because we want to draw the slip circle. Okay, the slip circle using the appreciate radius of the slip circle as a 12. So let's say you mark here from here 0 until here is a 12. You cross here and then at the same radius you mark from here to here, for example, as also 12. Okay, let's say we mark after we get the 12. So we have these positions as a C. Radius still equal as a 12 meter. Okay, now here 12 meter, here also 12 meter at O. So you can draw your slip circle using your jangka lukis. After you got that one, because the questions begins with answering by determining the locations of the tension crack, and you need to locate the depth of the tension crack where it is located. So the calculated Z node, when you go through to the next slide, Z node is equal to 2.5 meter. So let's say you have done that one, you dah calculate Z node, you dah calculate KA. And how to locate Z node on your graph paper? Okay, just starting at the C. Let's say we mark back. Okay, from here. Okay, from here to here as a C. Okay, you place your ruler at this position in the vertical limb at this point. This is such as 0 centimeter. You shift to the left side in the vertical limb. You might see, for example, from top to this slice, the slip circle out is just got 1 centimeter. You need to shift more until you have the vertical height is equal to 2.5 meter or 2.5 centimeter. So this is the positions of the tension crack as shown in the next slide where I draw it as a red circle. So what happened during this time? During this time, the tension crack will produce to you this circular length out. They give to you the CU is equal to 0. I mean that the strength of the soil is 0. What happened to the sector angle? Because this is the strength with a 0 value, the sector angle also changed to the new one as a theta C. How to measure that one? You just get from O until the end depth of the Z node. Here is a theta C. Right now, we have the new slip circle from OA to the D, for example. Actually, this one is a C, here supposedly as a B. Okay, after that, what we need to do is, because we are analyzing using method of slices, the next one, you have to divide the weight of the soil above the slip circle into equal vertical slices. Let's say we assume that the width B for each slice is a 2 meter. So you measure from A to here is a 2 meter. So mark as a slice number 1. Continue here as a 2 meter, slice number 2. Please be careful. The vertical height for each slice is bounded by the slip circle. They cannot beyond that slip 1. So this is supposed to be deleted. And the next, you measure as a 2 meter also, you mark to the next W. Same goes to here, the next W, and this one. Let's say for the last W here, this is the slice where the tension crack is located. So you might see that the B at the last slice here may not have same width as the previous slice. So let's say we measure it as a 1.0 meter because the B is reduced due to the development of the tension crack. So now we have how many W? W1, 2, 1, 2, 3, 4, 5, and 6. The next on this calculation is to determine the positions of the centroid of each WX. So when you call a centroid, the center of gravity for the soil mass, if you have the slice as a rectangular shape, so the centroid of the W is acting half of the width of slice 1 or any slices in the same shape. Exceptional for slice number 1 because slice number 1, as you can see here, this is the kind shape of triangle. So the W, let's say, is acting 1/3 from the base of the triangle. So this is W1. Okay, so for the slice number 2, 3, 4, and 5, the shape some sort of trapezoidal here. And assuming that the slip circle as a straight line at the base, so this is what we may have. So the W here, let's say, is acting at the half of the B. So the W is acting half from here is a 1 meter from left, 1 meter from right. So this is W number 2. Remember, in our table, the next slide showing to you that you have to find what is the B, what is the H1, what is the H2, and then the area for each slice, and you have to find the weight or the volume of each slice, and then the interslice angle. Next, calculate the T, disturbing force, and the last one is to calculate the resistance force N. The T is equal to W sine alpha and N is a W cos alpha. So what is a B? So again, B is considered as the width of the slice. So just now we say that the B is equal to 2 centimeter. Assuming that B, since you are divided the vertical slices into equal width, so slice number 1, 2, 3, 4, 5, we'll be having same B as a 2 centimeter from 1 to slice number 5. And the next one is what is H1? H1 for slice number 1, so look at to the slice of 1 here, is like a triangle shape. So you just letak your ruler at this point A. So you may start with a 0 centimeter. So we can say that H1 for slice 1 is a 0 cm. And then place your ruler at this position, the beginning of the height for the right side of the slice H1 until the end of this base here at the slip circle. That is a H2 for slice 1. Let's say we got a 2 centimeter. So you mark here 2 centimeter. This is my assumptions. Actually, you can get the right height using the ruler. So you ukur lah daripada tinggi ni sampai hujung slip circle tu berapa dia punya ketinggian dalam sentimeter. So katalah 2 cm kan kalau you dapat. So that's why I ask you to redo again. And then you can calculate the area for the slice number 1. For example here, the area for slice number 1 is a half times with the B times with the H1 plus H2. As you see here, this is the area of the trapezoidal. So half times with a 2 centimeter times with a 0 plus with a, just now I said 2. Okay. So that is the first area for slice number 1. And then for slice number 2, here, the vertical height at the left side of slice number 2 is becoming as a H1. Okay, now we go to the slice number 2, W2. H1 is equal to 2 centimeter because this is slice number 2. So just now H2 is a height for W1. Right now for W2, H2 just now is becoming as a H1 as a 2 centimeter. Okay, the H2 for slice number 2, so you ukur guna pembaris from top here until to the base of the slice. What is the vertical height? Let's say we got the 3 centimeter. So you mark here as a 3 centimeter. Then you can calculate the area for slice number 2. The process continuously until you got the final slice number 6. Okay, the slice number 6, as I said, is only difference to the B lah. So you can change the B, and same goes to the vertical height left and right side for slice number 6. And the next important part is on the what we call it as a YC. How to determine the YC. This is the last case where you have a tension crack full of water. Right now, we have additional force from hydrostatic. So the additional force is considering as a disturbing force, as a PW. The PW is acting 1/3 from base of the Z node. So 1/3 daripada Z node. From here to uphill of the slope is a 2/3 of the Z node. Okay, 2/3 daripada 2.5, so you dapatlah berapa kan? In order to get the YC, so YC is a height from 2/3 of the Z node plus uphill height 2O. So we remark as a Y prime. So YC is equal to 2/3 of the Z node plus dengan Y prime. Y prime ni you kena ukur guna pembaris daripada uphill slope sampailah O ni berapa tinggi dia. That is your Y prime. So the formula to calculate FOS for last case is that so kita akan dapatlah restoring moment over disturbing moment is equal to T plus dengan PWYC over R. This is the appropriate disturbing moment component to the last calculations. Is there any questions? On this part, this actually is a graphical hands-on calculations. So you have to make your own exercise to ensure that you have understand on this matter, so you are able to conquer the subject in the slope stability analysis. Do you have any question?
Not yet, madam.
Okay, this actually, if you got the hands-on and hands-out from here, there are many examples available there. If you feel that you could not done it alone, you can have a group discussions. Online group discussion like this, you on each camera, everyone on camera, turn on the camera, and then check how to construct the graphical slope using the graph paper, and then discuss how to fill up in the table, tabulate the table, find the A, find the H1, H2, and then finally calculate the W. Other than that, I almost forgot about the alpha. Alpha is another important thing. Alpha, as I mentioned earlier, it is an interslice angle between W and the normal force. So remember, when we take out the interslice of the slip circle, this is, for example, what we have. So let's say the W is acting 1/3 from the side. Okay, where is the alpha? If you have this of O, the center of the slip circle, and you got the W here, so the alpha is taken from the O to the base of the slip. So this is quite missed. So here is the positions of alpha. Alpha can be taken as a positive side and also can be taken as a negative side or negative value. So look at to this one, to the W1. The W1 is located here, and this is our O, the positions of O. So you take from here, from O until you meet at the base of the slice 1. Okay, meet to the vertical wake W1, and the angle between W and the tangent line from O here, that is considered as a interslice angle, alpha. If the alpha located on the left sides of O, so the alpha is negative. Okay, look at to the slice number 5. Here slice number 5. So we have divided half from 1 meter left, 1 meter right. So this is the position of the W5. Okay, look at to alpha W5. From here, O until the baseline of 5 here. So we take it from here until we meet the baseline. So actually, this is the N component. Okay, the angle from the W to the N component is the alpha. And if you see here, the W5 is located on the right side of O. Thus, you can have that the alpha is a positive. So what's the effect? The alpha, whether it is positive, negative? Of course, yes, when you substitute in this formula. If you have the fifth alpha such as positive 15 for W1, if you have alpha for W5 positive 15 degree, and let's say you have W1 alpha is a negative 5 degree. What's the effect? The effect when you calculate this one, such as if you want to calculate T1 for slice number 1, you may have that W1 C alpha negative 5. So when you calculate this effect, sine negative 5 and sine positive 5, also cos negative 5 and also cos positive 5. Same goes to N1. N1 is a W1 cos negative 5. What's the answer? You can see that if you have the angle is a 15, so you substitute T5 for slice 5 is equal to W sine positive 15. And then for the N5, you may have that W cos positive 15. So the total of the summations of the component T and component N will be affected due to the sign positive and negative. If you have positive, so you can adding all. If you have negative, you have to minus. So that's the importance of the negative positive of the alpha. So please be careful when you have the W for each slice, whether it is located on the right of the O or at the left of the O. If you have the W on the right side of O, so the alpha is positive. If you have W on the left side of O, so the alpha is negative. What is the O? O is the center of the slip circle. Whether you have tension crack or you don't have the tension crack. Any questions? Okay, I think that for this moment a bit tough for you to understand unless you can have your own exercise first. Go back to the example 2 and any examples, do it hands-on and then check the formula, tabulate the table. So you got familiar to this kind of question from example 1, 2, 3, then it's develop your understanding on the subject matter. Okay, any questions? Do you have any questions? Okay, I assume.
So far not, madam.
So far not. Thank you for responding. Actually, it's a bit tough. If you feel that the learning is tough through online, same goes to teaching. We are facing challenges and issues, both of us. I tried my best to give you understand on this matter graphically online using the online whiteboard, and then you are difficult to get the informations through online, but how to make that once easy, try and redo the examples given here. I think that the best one lah, because as I said earlier lah, because this is a part of the topic, a part of the topic in the assignment 1. Sebab dalam assignment 1 macam saya cakap lah, dia akan cover topik 1, dia akan cover topik 3. Topik 3 pun banyak method kan, kita banyak examples. Buat semua example, cover semua example, semua method total stress analysis, effective stress analysis, Fellenius, Bishop, supaya you betul-betul yakin, you faham. What's the important thing is that when you are, let's say in the future, in the next 5 years or in the next 2 years, who knows, you are becoming or you are working in the consultant firm, or you are working with the top companies such as Gamuda or KLCC project, and you need to deal with the slope stability. Even though if you work with the plus highway, you are the major projects, you are dealing with the slope reinforcement, slope protection, slope designs, and this is the time when you reuse back or you get all the informations you have learned on the slope stability to what we call it, to design and to analyze during the time. So if you really not get through to understand on this topic, how to start the first analysis of the slope without having any tool in technology such as computer programming or computer software. So the best answer, the best hand calculations is the good teacher for you to first develop understands on any topics given to you. For me, it is better for you to start off using hand calculation, expert with the Excel, and then go to the advanced technology. So the understanding the concept, the theory is help you to do the next analysis and design. Please take your time, go through these topics 3 and do group discussions on how to analyze it. All the best to you, and we see you in the next class. Okay? Right?
Okay, madam.
Okay,
Okay,
thank
madam.
you. Okay, Assalamualaikum.
Thank you, madam.
Thank you,
Thank
madam.
you, madam.
Thank you, madam.
Thank you, madam.
Thank you, madam.
Madam.